I started with basically telling you about how basically nature makes very selective compounds by using complicated organic compounds in which basically the combination of scaffold, functional group, and stereocenters basically code in a way for a three-dimensional structure. And that is similar to how basically nature codes for the structure of proteins by having the information in the sequence, amino acid sequence. With organic compounds, nature uses a more complicated approach to basically code for the structure and function of these compounds. And we just basically do it in a different way. We take a metal center, and the coordination bonds, the coordinative bonds, they basically more or less, of course, in combination with the structure of the ligands, they code for the three-dimensional structure of these compounds. And when you look at the space-filling model of this PEC1 inhibitor I showed you and galdanomycin, you cannot say that the one is more complicated than the other. They are both complicated three-dimensional structures, have very defined shapes, and therefore also very defined biological activities. And so that is basically our approach, and we apply to protein kinases because there are so many protein kinases, more than 500 encoded in our genome. It's a huge challenge to inhibit individual kinases, but not the other 499. And of course, we want to apply this concept also to other enzyme families where you have selectivity problems like proteases, phosphatases, and so on. And that's for us, of course, very exciting. And we hope that in the future that such scaffolds will also be used in chemical biology more frequently, and will also find their way into medchem, into pharmaceutical industry. We are convinced that in 20 or 30 years, such metal scaffolds will be very common scaffolds for the design of drugs, and we will not be limited anymore to these very simple and not that sophisticated organic compounds. And maybe at the last minute, I want to maybe point out one problem. And I told you that we have, of course, this sophisticated metal center that gives us all these options to build structures. We have 30 stereoisomers in a worst-case scenario with 6 monodentate ligands. But the question is, how can we control the formation of these stereoisomers? We cannot synthesize compounds, make all the 30 stereoisomers, and then separate them. So the reason why actually this is quite an enormous challenge is also we have to basically find ways to control the stereoselective synthesis of such compounds. And you're aware of the fact that in organic chemistry there are hundreds, if not thousands, of groups caring about the stereoselective formation of one stereoisomer at carbon over the other. And now we are saying we need methods that allow us to form one stereoisomer out of 30. That is, of course, a problem that is orders of magnitudes actually larger. And to give you an example, this simple compound, it's just a ruthenium compound with 3 bipyridine ligands. Actually, this compound can form, it's a very simple compound, high symmetry, it can only form 2 stereoisomers. One so-called delta enantiomer and one lambda enantiomer. And basically you see there is basically kind of a screw sense here. So you have a right screw and a left screw. Until recently, actually, it was not possible to synthesize selectively one enantiomer over the other. This seems like a simple problem, but everybody had to separate these racemic mixtures. So people made these compounds as racemic mixtures, and then they separated this racemic mixture by chiral method, chiral column, chiral counterion, and so on. And that shows you how far we are behind in the stereoselective synthesis of metal compounds. And we think that stereoselective synthesis of metal compounds have to go hand in hand with, of course, the evaluation of their biological activity. This is the same with organic chemistry. If we would not be able to do stereoselective synthesis of organic compounds, we could not make complicated bioactive organic compounds. So we started a research program in our group that really aims in controlling stereoselectivity, and we saw this is actually a nice test system. Can we find ways to make this compound stereoselective in an enantiopure fashion? And we developed actually a very simple a strategy that is used actually in organic chemistry every day, and that is the use of chiral auxiliaries. So the idea is we want to use a chiral bidentate ligand that is in the coordination sphere somehow, and then controls the incorporation of additional ligands, so the ligands exchange reaction, and can later become removed. That is really the same way as we use chiral auxiliaries in organic chemistry. The problem that we had to overcome is with a metal such as ruthenium, and we work actually in all our compounds, we are interested in chemically and substitutionally inert metal compounds. If you use bidentate ligands, they stick very tightly to the metal. So once you incorporate them into the coordination sphere, can you get rid of them later without basically compromising the chirality at the metal? So, my student Lei and Sean, they actually developed something very nice, which we published this year in JACS a few months ago. We use these, which we call salicyl oxazolines. You can see here an oxazolene and a phenolate, and it coordinates as a bidentate ligand to the ruthenium. So you have an O- and a nitrogen. And in alpha position, we have here a chiral group, which is derived from a reduced amino acid, an amino alcohol that forms this oxazolene. And as you can see here, this isopropyl group really basically comes in close proximity to these two coordination sites. So if we have 4 leaving groups, what happens is that the first bidentate ligand basically tries to fill the coordination site that is the farthest away from this isopropyl group, that is this coordination site here, and then the remaining coordination site is basically left for the second bidentate ligand, and this way basically the absolute configuration at the metal is determined. And luckily with this ligand we can remove this ligand by adding acid and protonating this oxygen here, decreasing the coordination strength of this ligand. So in presence of TFA, just a few equivalents, we can remove this ligand and replace it actually in a one-pot reaction directly with a third bidentate ligand, and we can obtain this compound in a basically more than 99.5% ER ratio, basically practically in enantiopure fashion. And that shows you basically how we think about doing stereoselective coordination chemistry at metal centers, and we're actually very excited about it. And our goal is to be able within the next few years to synthesize stereoselective compounds that are as complicated as, for example, this compound here, FL, which we call FL172, and that's still an enormous challenge, and we are not there yet. Okay, I hope you enjoyed this short summary of our efforts, and I hope that more people will use in the future metal compounds for the design of bioactive compounds, in particular enzyme inhibitors. Thank you.